Royal Astronomical Society of Canada, Ottawa branch. I'm Mick Wilson. I am the MC for tonight. I'll be doing this introduction, some brazen pleas for joining membership and giving us money and stuff like that. Andrea will also have a brief natter about the opening of submissions for the RASC calendar for 2025 and the conditions and protocols for that. Dave will descend from on high and give us the update on Ottawa skies for this month, plus a couple of other tidbits. Rick Wagner will follow up with less current news, but potential news regarding T Corona Borealis. I will get to have a bit of a rant. I made a terrible mistake last meeting and not only let it run too long, but I let other people speak before I did. And so I'm making up for that and getting in first this time. Simon is bringing up the very interesting topic of glaciers on Mercury, the break, trivia, door prizes. Jim Thompson, is he here? Okay, good. Doing his favourite thing about telling us about favourite technologies. Dave and his low-cost Eclipse projection rig. Then we get the observation reports. Richard, where are you? Richard Taylor has stepped into Oscar's gumboots and is going to introduce us to a new variation on the monthly observing challenges with a live follow-up after the show. So stand by for that. And then we close out with the usual announcements and so on. So Andrea? Oh, hang on, sorry, I did need the usual caveats. Yes, we are recording this. If you've got a problem with that, don't say anything. If you're online, please use the Q&A rather than popping your hand up to ask questions. And the raise your hands is disabled. Yeah, please, Dave. We had 8 new members in January. We didn't get an update from Chris, who's not with us tonight. Any of Margaret, Malcolm, Emily, Anna, Christina, Jerry, Gilbert, or Nicole with us tonight? Who? Yay! It's good to get some live new members sometimes. Next one, please, Dave. Okay, so here's the shameless plea for money. What are the benefits of joining RASC Ottawa? Next, please. Next, please, Dave. My favourite selling point are the people in the club, the expertise, the experience, the people you can go to with the most naive and basic of questions and not have them laugh you out of the room, through to technical experts dealing with advanced technologies and so on. We have the guest speakers coming in who are, in many cases, the highest calibre operators in their particular domains, whether that's planetary science, astrophysics, or what have you. So make the most of the personnel benefit of being a member. Physical benefits, access to the Ted Bean Loan Library. There's well over 100 telescopes for you to use, either if you're considering buying into astronomy hardware or upgrading from where you are at the moment. It's all free for our members. There's a media library out the back with books, DVDs and so on. That's a Stan Mott library. There's Estelle here. Hi, Estelle. So she'll be opening that up behind the curtains. It's a bit like Wizard of Oz. And that will be during, after the show this evening. During the break as well? I don't know, does anyone want it during the break? Anyway, after the meeting, that'll be available to you. You will receive the Journal of the Royal Astronomical Society. It's a bi-monthly, fairly serious sort of publication. The Observer's Handbook for 2024 is, yes, still available. It's a long sought after compendium of everything you need to know as an observer. And then there's our own fabulous local newsletter, Astronautes. Is Gordon here? Gordon is not here. Okay. That means I can embarrass him. As a member, you'll also have access to our Discord server. If you're not familiar with Discord, it's an online chat facility. It's less formal than the structured email mail outs that we do. And again, it's another avenue through which you can ask a question, seek answers, try to organize group activities. And there was a particular point that Andrea wanted me to make about the URL or the invitation. Can you remind me? Okay. And it will be in Astronotes. Thank you. Yeah, well, yeah, we'll have to fix Gordon. So you get all these luxury items at the very reasonable price of $103 for a normal membership, $100 plus a few overheads for a family group, and $62.40 for students or anyone under 21 years of age. And that in this day and age is an absolute bargain, ladies and gentlemen. And Dave, next please.
Hang on just a second, Mick. I'm just going to stop sharing and reshare so we try to get the remote working. Just give me 2 seconds.
See, things go much better when Chris is doing this. Nope. Okay. Did you do that or me? Okay, so Andrea, please.
Hi. I just wanted to let everybody know that they've opened the submission window to submit your image for the calendar. If you are a RASC member, you should have received an email this morning from RASC National. There is a link in that email and if you follow it, it'll take you to a document called the Image Guidelines. And there's a link within that document to submit your image. We did really well last year. We had 3 images from Ottawa in the calendar, and so we want to do more this year. The important thing is that you must be a RASC member to submit the image. There are some sizing requirements, but other than that, send your nicest pictures in. There's also a link in the Discord.
Okay, thanks, Andrea. Any questions? Okay, Dave, come down, join us.
Actually, I'm going to stay up because the slide advancing is not working.
Anyway.
So you can just imagine me down there. How's that? So let's take a look at the Ottawa skies for March 2024. Here are the moon phases. March 10th is the new moon. And on March 25th is the full moon. It was known by the early North American tribes as the worm moon, because this is the time of the year when the ground would begin to soften and earthworms would appear. This moon has also been known as the crow moon, the crust moon, the sat moon, and it is the Lenten moon. Easter is defined as the first Sunday after the first full, after the 21st of March. Okay, so let's move on. We also have daylight saving time, which didn't seem to fit properly on the screen. Okay. As you can see, the days are getting longer. We have the greatest eastern elongation for Mercury on March the 24th, but either side of that date, you should be able to see the planet low in the western sky just after sunset. Venus is not visible, and it's rising and setting with the sun. And Mars, sorry, I don't know what's happening with these slides here. They're scrolling a weird way. It's not visible as well. Jupiter is visible in the early evening, and Saturn is not visible. Uranus is visible in the evening, and Neptune is not visible. And here is our cartoon of the month. Sorry about that, Mick.
No, you're not.
So I've got
Crikey,
I got 2 others, 3 other slides after this one. So I'll just move forward. So on February the 22nd, you may have seen my picture on the front page of the Citizen. He did a pretty good job of capturing the stuff that I gave him for the solar eclipse. And yeah, it was lots of fun to do that. A group of us met. I sent out a general invite to everybody, but a small group of us met with Dr. Sarah Seeger the day before she received the Order of Canada. And here's a picture of us at the Lord Nelson Hotel. And then here is the actual presentation.
Sarah Seeger. Astrophysicist Sarah Seeger has transformed the study of extrasolar planets into a full-fledged planetary science. By developing a new comparative and interdisciplinary approach, this MIT professor pushed the limits on how astronomers study distant planets and how they could eventually detect signs of extraterrestrial life. As a leading force behind large-scale projects handled by NASA, she is a trailblazer for women pursuing studies in the field. Your Excellency, Dr. Seeger.
All righty. Thank you, Dave. Richard.
Depending on them for slide changes.
Yep.
Okay. So this is my first time back at an in-person meeting here in a long time. It's nice to be behind a podium looking, well, kind of dark, but your smiling faces up there. Not having audio and occasional freezes of the video feed, but we don't have to worry about that anymore. So T Corona Borealis is a recurrent nova. Next slide, please. So what is it's a part of a larger group called cataclysmic variables. Basically, on the left we have a white dwarf or some other compact stellar object, like perhaps a neutron star or something. On the right-hand side, we have a much larger star, perhaps a normal main sequence star, red giant, red supergiant, something like that. And the two of them are close enough together that the white dwarf is actually sucking material off the surface of the larger star. And it doesn't just fall from the large star to the white dwarf. It actually swirls around in an accretion disk, and all this material, it doesn't rotate as a rigid disk. Of course, it's rotating slower at the outsides and faster on the inside, and so all that material rubbing against each other, it gets hotter and hotter as it approaches the surface, and then finally impacts onto the surface of the white dwarf. And what happens is most of this is hydrogen, and it builds up and builds up and builds up until it gets to the point where the material at the bottom of this layer actually gets hot enough to start thermonuclear reactions, combining the hydrogen into helium. And because there's this huge amount of hydrogen piled on there, you get a thermonuclear runaway, and the whole thing just goes pow and explodes. And mostly what happens after it explodes, we're back to the same situation. The hydrogen starts building up, and sort of some thousands, hundreds of thousands, million of years later, it blows up again. However, there are a few of these stars that are called recurrent novae, and they start doing it. Anything that's happened more than once in 100 years, we call a recurrent nova, in spite of the fact that they all probably recur. And in fact, there's one in M31 that they find goes off every year. So basically, it's the timing of the flow, the quantity of the flow, and so forth that determines how often they recur. So next slide. So this one went off in 1866 and was noticed. And what's really interesting is there are two famous people in the process of finding this. One was the last guy to notice that it wasn't visible, Julius Schmid. And he was actually out observing. Back in the old days, a guy could look up at Corona Borealis and be able to say that at such and such a time, I know there was no star there. And 2 hours later, a guy in England is saying there is now a second magnitude star there. So that's what happened. And that on the left is the 1866 observation. So these are data from the AAVS, the American Association of Variable Star Observers, their international database of variable star observations. So you can see there's this very sudden peak. For some reason, Leslie Peltier, who you may have heard of, wrote a book called Starlight Nights. Anyway, he decided that this thing was probably going to go off again, and he started observing it and watched it every night he could watch it for 40 years or so, until one morning in 1946, cold February morning, he decided he'd rather just sleep in rather than get up and look at the stupid thing. And of course, pow, off it went. And he missed it. And he kept observing it, but he said, we had a close, intimate relationship for 4 decades. I don't trust her now. Well, of course, she was being seen by other men. So anyway, so 1946. So that's about 80 years. 80 years from 1946 is 2026. So we can expect that there should be another eruption coming in a couple of years. But the interesting thing is, if you notice, this is data right up to like a few days ago. You notice how it goes along, and then suddenly there's a jump. And that was about 10 years ago. It suddenly brightens by a magnitude. And that's what it did 80 years ago. And that's what it did 160 years ago. And it's done it again. And then about a year ago, it suddenly drops off by a magnitude or two, which it did 80 years ago and 160 years ago. And that happened about a year ago. And that usually happens about 1.3 years before it blows up. So guess what? The prediction right now is that this thing is going to blow up at 2024.4 plus or minus 0.3, which is May plus or minus a couple of months. Next slide, please. So if we zoom in closer on just sort of the last 20 years of data, you can see back 10 years, it suddenly went up, and then it goes down and then drops off. These are, the first ones were all visual magnitudes, all done by visual observers, just with a binoculars telescope. This is B magnitude, so most of these would be photographic plates, but the later ones are CCD observations, mostly by amateur astronomers, and in blue wavelengths. And next, please. No, other way. Okay, so now you can see this is the part where it's at the elevated brightness, up about a magnitude, and you can see that there's some sign of an oscillation in there. And what that in fact is that the white dwarf is close enough to the red giant that it's actually stretching the red giant tidally out into like a shape of a football. And so you can imagine that when the football is pointing at us, we are seeing less surface area of the star, so it's a little dimmer. When it's side on to us, we're seeing more of the surface area of the star, so it's a little bit brighter. This is called an ellipsoidal variation. And you can see that it goes on, and they're actually measuring this and determining how often when these peaks actually happen. And the peaks are actually changing when they're happening. The period is changing dramatically, like to the point where they've done the calculations to try and figure out how the star is working. And this thing is changing something like 100,000 times faster than they can explain. So at any rate, it drops off and it comes up basically to yesterday morning. I checked it, it was 10.5 again, according to my estimate. Next, please. So the thing we want to do is we want to get as many people observing this as possible. If we can catch it starting to rise, everybody can start observing it. We can catch it going up. It takes a few hours to go from 10th magnitude to 2nd magnitude. It takes about a week to go back down below naked eye visibility. If we get a bad week of weather, we might miss the whole thing. But we won't do that, will we? So the thing to do is to try and do a proper scientific, useful observation of it every time you can. You go to the avso.org website, you click on Tools and Observer Resources in the center there. Next, please. And that takes you to this page. Now, at this point, you're going to need an observer code from the AAVSO before you can submit official observations. But that's easily done. You can go through the new observer start here. But assuming you've already got a code, click on VSP, the variable star plotter. Next, please. That gives you this page, how to plot a chart that will give you the magnitudes of various stars in the area that you can compare T-Corridor against. So a lot of stuff to put in there, but most of it you don't have to touch. T-Corridor at the top. The third one down, you choose the scale of the chart you want to look at. An A scale is best for naked eye or small binoculars. An AB scale is best for small binoculars, and a B scale is best for binoculars, decent sized or large binoculars and small telescopes. Everything else, the defaults should work fine for you. Next, please. So this is the A chart. You can see I've highlighted in the lines there to show Corona Borealis better. The star itself is the little circle with the crosshairs in the center. And all those numbers are the magnitudes of stars in the field minus their decimal points, so we don't have all those little fake stars in there. So basically, the simplest observation you can do, and this takes like half a second, is you look up at the sky. Is there a star just off the side of Corona Borealis? There's nothing else bright in that area. If there's nothing there, look around the stars of Corona Borealis and see what's the faintest star you can see. So let's say it's the 4.2. Now I can go to the AAVSO. I can report that T-Corridor was fainter than 4.2. So we know, A, that it hasn't erupted yet, and B, if somebody else has accidentally reported incorrectly that it has exploded, it will save a huge cost, because there are literally thousands of astronomers, hundreds of telescopes and satellites that will all slew into action the instant this thing blows up. There are millions of dollars. Plans have been going, for a year or more. Hubble Space Telescope, JWST, X-ray telescopes, infrared, the whole thing. The whole world astronomical world is going to erupt in activity when this thing goes off. So the idea is you make your report that it's fainter than 4.2 at such and such a time, and that way we know nothing's happened yet. Next, please. This is the B level chart. So you can see this is about 3 degrees from top to bottom. There, 4.2 is one of the stars in the circlet of Corona Borealis. And now I draw on my own little constellation just so I can track the field. It means that I can get out, with my telescope, and in a couple of seconds I can look at it and say, okay. Now on this chart, generally what you're going to want to do is, like with a 6-inch telescope or something, or large binoculars, you might be able to see it. You're actually going to try and estimate. So for instance, right now I look at the 9.8 and the 10.8, and I go, it's probably 3/4 of the way, in brightness from the 9.8 to the 10.8. So that makes it about a 10.5 magnitude. Next, please. So you go to aavso.org/webobs. This is their web observation reporting thing. it's a visual observation. You put in the star identifier on the next line, the date and time. If you know the Julian date, that's fine. Otherwise, you do YYY/MM/DD and so forth for the date and time that you observed it. What magnitude you measured it at. There's a little checkbox. If you didn't actually see the star, you can say the faintest star I saw was such and such, and the star was fainter than that. First comp star is the star you were comparing it to. Second star, if you were actually estimating it in a range, that's the other star. And then the chart ID comes from the top right corner of the chart that you got from the AAVS. So that way they know which comparison stars you were using and so forth, so that they can, if there's corrections to magnitudes and stuff, they can fix stuff like that. And if you're like me and you get up a little too late in the morning, you can click on that the sky is bright, moon, twilight, and stuff like that, because right now it's sort of 5 o'clock in the morning. And that's all it takes. I think that's all I have. Next. We're done. Any questions? Yes. With a telescope, it's about 10.3, 10.5, depending on who you talk to. I try and get up every morning when it's clear at about 5 o'clock, get out the 8-inch telescope, do a visual observation. And if it's clear out, I'm also running it and doing CCD observations. They actually prefer visual observations because not only does the star go through this ellipsoidal variation with a 227-day period, but it's also flickering. As that material flows off the red giant and onto the white dwarf, it comes in clumps. It doesn't come as a nice gentle stream. And so the star is continually flickering all the time. And so with the CCD observation, sure, you may get 1/100th of a magnitude, but that's, you know, the brightness that it was at some instant in time. It's not a good guideline as to, you know, sort of the going brightness of the star currently. So you could be famous. You could be famous if you're the first person to see it blow up. You could be famous if you're the last person who didn't see it. Thank you.
Okay, I assume we're still technology bound. Did I get it back? Okay, anyway, next slide, please, Dave. Alrighty, I've been described as sometimes using colourful language, and so I thought it was appropriate to introduce a new example of that. This next little 3-minute thing of mine is an example of spitting the dummy. For those of you who have never gotten out of North America, a dummy is what you up here call a pacifier. And the mental image is one of a very upset little child who's so upset that the dummy is gone and now they're even more upset. So this is spitting the dummy. Dave, lead on. So bloat, I'm here to talk about bloat. I find bloat to be a complete pain in the abdomen and is the bane of my life. Next, please. In the normal world, I find bloat is particularly caused by IPAs, hence I'm no longer drinking IPAs, but that's not what I'm here for tonight. Dave? My real pain in the abdomen is file bloat, and I'm here to plead with the contributors to our meetings on this very topic. Next, please. Please reduce image sizes. I'm asking this with thanks in advance, humbly as your webmaster. Next, please. Do not mistake this for a lack of gratitude to the degree of effort, professionalism for a bunch of amateurs, the long hours, the care to detail and process that I know goes into many of these products, and that the level of pride and fulfillment in presenting them to your peers is something of which I can only be jealous. Yay. However, Next one, Dave. As a webmaster, I have to be a bit of a web Grinch. Next, please. Our hosting service is something that we pay for. The website does not come for free, and the more we scale up demand, the more it costs the centre. So there's an incentive to keep those growths in demand for storage and bandwidth within manageable bounds. Next, please. Face it, the facilities that we have here have limited resolution. You might be very, very proud of a 4K wide image, but no one's going to see it on this screen with this projector. Please bring it down to the sort of scale, 1800 by 1200, somewhere around there. It cuts the file size by a factor of 4. No one is going to see any degradation, either on this screen or, next slide, Dave, on their monitors at home, or least of all, next one, Dave, least of all on mobile devices, where, to add, a bit more pain to the equation, they're probably, possibly at least, almost also paying for bandwidth. So, Dave. Most personally, I spend a heck of a lot of time each month going through and having to do the file reduction myself. Yes, we could buy a utility to do that, but again, that comes at a cost to the centre. And so that's an extra effort on me, and I'm just getting older and older. Next, please. Next again. So, on behalf of your aging webmaster, help me out, use Google Slides to get stuff to me, and beforehand, please do some file reduction, get the image size down to something manageable. If it comes out more than about 6 megabytes, it is generally of limited utility, and I will have to put in more effort on my part. I would rather distribute the load. So, thank you, Dave. Yeah, I know, that was in Africa too. Everyone's cuter in Africa. Okay, so then, Simon.
Just in time for Simon, we've got the remote working.
Let's prove it. Hey, whoa, what was the problem? Okay.
Okay, so which
big
is
green, big green.
big green one is okay, and which one's the pointer?
Laser.
That one's the laser.
Yeah,
Let's have a look. I don't see any laser there.
Oh, that one, that looks like a
That
laser.
one there.
Yeah.
There we go. Okay, very good.
Best.
Okay, let's see what happens, shall we? Well, as Rick said, it's a real pleasure to be back in front of a microphone and in front of all of you. But we do get used to the fact that you can actually attend these meetings in 2 different ways. And my wife caught on to that. And so she's watching this evening, so I've got to be on my best behavior. And I just wanted to say, hi, Mila. Okay, enough niceties. Good, I can see it here. All right, Glaciers on Mercury. Now, as many of you know, I follow the scientific literature on planetary geology, both as a professional geologist, albeit retired and recycled, and as an amateur astronomer. And much of the scientific literature tends to be more of the same, with young scientists simply reiterating what the scientific community already thinks it knows, but in a slightly different place or from a slightly different perspective. However, every now and again, a paper pops up that really sets me back on my heels and proposes something really different. Something that makes me say, goodness, I had no idea, or less repeatable words to the same effect. Now, one such paper came to light recently concerning the planet Mercury. It's entitled Mercury's Hidden Past, revealing a volatile-dominated layer through glacier-like features and chaotic terrains, and it's by Rodriguez et al., group of publishers, of authors, published in the Planetary Science Journal last November. So it's new stuff. Good. Now, just hang on a minute here. The daytime temperature on Mercury can reach 400 degrees C at the equator. So why would anyone think there are glaciers on this planet? Well, it all depends on what we mean by glaciers, which explains the quotation marks in the title of this slide. Now, geologically speaking, the term glacier can apply to a sheet of something solid that flows on the surface of a planet. Most folks, when they think of glaciers, think of ice, but other stuff can flow like a glacier too. Now, one of the big surprises from the Messenger mission that entered orbit around Mercury in 2011 was the presence of bluish patches, which you can see very clearly on this slide, spatially associated with small pits. Notice the scale bar, it's about 5 kilometers. So these are small, and they generally occur inside impact craters. They're referred to as hollows, and they're interpreted as pits that formed when the volatiles stored beneath the planetary surface sublimated, just like the ice and snow around Ottawa is sublimating without melting right now, leaving underground voids into which the surface materials then collapsed. Now, I presented a talk that touched on this to the Ottawa RASC in 2019, but you'll have to go to my personal website to find it. And that website is Simon Hanmer, one word, or rather Simon Hanmer 52, one word, .ca/presentations. But what volatiles are we talking about here, and why did they sublimate? And what's this got to do with glaciers on Mercury? We'll get to that shortly. Now, the authors of this paper on glaciers investigated two types of terrain near the North Pole of Mercury. The first was located in a couple of impact craters, Raditladi and Eminescu, which is shown as those black ellipses in this image here. And the second is a vast irregular patch, it's in red on this image here, of chaotic terrain called the Borealis chaos, northern chaos. Notice the scale bar here. That's 500 kilometers. This is over 1,000 kilometers long. Press the right button. Now, back in 2008, just after a messenger flyby of Mercury, I presented a talk to the Ottawa RASC, but you'll have to go to my personal website to find that one too, telling you that one of the characteristic features of impact craters on Mercury is that so many of them have central peak rings as opposed to simple central peaks. I think that the central peak ring here is pretty obvious. It's this thing here. That is the outer wall of the crater. Now, they occur on the moon too, but they're much more common on Mercury. It's all down to the velocity of the impactor, which is a partial function of the gravity of the body being impacted, which is greater on Mercury than on the moon because it has an anomalously huge iron-nickel core. Now, if you go to my 2003 presentation to the Ottawa RASC, I described this in some detail. And yes, you'll have to go to my website to find that one as well. So why am I telling you all this? Well, let's go to the next slide and find out. To understand why glaciers on Mercury might be linked to impact craters, let's take a closer look at Raditladi crater. Now, at the top left, that's this image here, is the peak ring of Raditladi crater. And you notice that lobate brown patches around the foot of the peak ring. There's these brown patches here, and they're lobate. These are referred to as flows or runouts. I'll explain that in just a second. Notice also the scale bar, 30 kilometers, and the white boxes, B and C, there and there. Now, at top right and bottom left, top right, bottom left, are detailed images of those white boxes B and C. Again, notice the scale bars, 5 kilometers, so we've zoomed in close. And in both images, parts of the peak ring are seen at top right, and the flat floor of the impact crater is to the lower left. So this is part of the red here is part of the high topography of the peak ring, and this is the floor of the crater. Same thing here, peak ring, and the floor of the crater down here. And the edges of these runouts are indicated by yellow arrows. Those are these things here. That's my water bottle. So I dry up. These yellow arrows here and these yellow arrows here, they're showing you that this is, in fact, the edge of the lobate runout. And then there are also red arrows, these little arrows here and here. And they're pointing to examples of groups of sublimation pits or hollows. And the important thing is that they only occur on the surface of the runouts themselves. Finally, notice that black lines X prime, Y prime, drawn across the two runout examples, and the diagram at lower right shows the topographical profiles along these two lines. And notice that both profiles are convex upwards like this. That's important. And that they abruptly drop down to the crater floor as they terminate at the left. It's really quite nicely shown on this one here, but also there. Now, the authors of this paper suggest that these runouts, some 10 kilometers in horizontal length, that's that dimension there, by about 200 to 250 meters in maximum vertical height, in other words, the thickness of the stuff in the runout, shows the same topographical profiles that one would expect to see at the edge of a crater, a glacier of flowing ice. Well, I've seen the edge of the Greenland ice cap, and indeed they are right. Look at the shape of the edge of this ice glacier. It's convex up on top, and it terminates quite abruptly as you come to the terminal slope. They, the authors, suggest that these runouts on Mercury are some kind of volatile rich material, hence all the sublimation pits, that flowed from the tops of the peak ring down to the floor of the impact crater to form the lobate deposits. That's these brown lobate flows here. Deposits that look very much like glaciers of ice on Earth. Okay, but what's the causal connection with impact craters? Well, when a bolide, by bolide I mean an asteroid or a comet, hits a planetary surface, its kinetic energy, the energy of motion, is transformed into the energy of heat. And that heat is therefore localized in the center of the impact crater, right under where you'd expect to see the peak ring. So the idea is this: before impact, there was a volatile rich layer of something buried just beneath the planetary surface. And it's indicated here by VRL, volatile rich layer. When the surface was impacted, heat was generated in the central part of the crater as the peak ring rose up in response, mechanical response to the impact, thereby uplifting warmed up and softened volatile rich material and providing a slope for it to flow down. And here is the cross-section we just looked at, plus the sequence of events during the formation of an impact crater on the right. Notice that the scales here in both directions are in kilometers. So the height of the peak ring is not very pronounced in these images, but it is high enough to give us the slope required for something warm, soft, and volatile rich to flow down. So here you've got the overall crater. This is the peak ring. This is one edge here showing you that it's hotter actually in the core of the crater than out away from the margins. The peak ring would be somewhere here. And this is a sequence of events as things collapse. And the peak ring would be about there and there. It's tiny in that diagram, but it's actually quite high. Now, we have to ask, so is Radit Ladi crater just a one-off, or is it just weird? Or are we looking at something systematic here? Which is why the authors then looked at Eminescu crater, which is reasonably close by, which has a somewhat smaller peak ring. That's the peak ring in Eminescu, whereas that's the outer wall of the impact crater. Well, it certainly does look as though it shares the same features as Radit Ladi. Here are the lobes, like runouts at the foot of the topography of the peak ring. So we seem to have a pattern developing here. Now, interestingly, when we look at the topography of the main rim of the impact crater, which is shown up here, there's the outer rim, and that white box there is this area right here. This is an example from Earth. I'll come to it in just a second. And with respect to the outer wall, the outer rim, we do not see the same features. The white box is here, This is a run out, if you like, from the steep wall, but it actually looks like something like this, which is just a standard classic common or garden landslide. We don't see any of the pits, sublimation pits there at all. It's just a standard terrestrial landslide. So there's clearly something strange going on at the peak ring itself. So, okay, something warm and soft with lots of volatiles was flowing from the upper parts of the peak ring topography down to the foot of the slope and out onto the crater floor. You can see that illustrated here. There's the peak ring or a segment of it. Something up here is warm, partly it's partly molten, if you will, and it starts to flow down towards the floor of the impact crater. So what was it? What is this stuff that flows to form these glaciers? It may look like a glacier, it may quack like a glacier, but not at more than 400 degrees centigrade. It's not a glacier, not an ice glacier. So planetary scientists have kicked around a number of candidates to explain the bluish sublimation pits. There they are again. I've just turned the figure you've already seen on its side. They kicked around a number of candidates to explain these pits, which were, of course, discovered over a decade ago. And the candidates include sulfur, carbon, graphite, chlorine, sodium, potassium, all volatile substances, but none of these is viscous enough under the surface conditions of Mercury. They'd be too runny. They wouldn't form these lobate flows. However, salt, which is sodium and chlorine, NaCl, common table salt, could fit the bill, and it is volatile on Mercury. So, okay, salt. But what's salt doing on Mercury, and how widespread is it? This is an important question. On the left is the author's cartoon, here from top to bottom. The author's cartoon of the geological setting of salt on Mercury. In slice A at the top, it shows an ancient body, an ancient buried rocky basement that's covered by a younger layer rich in salt. So there's your buried rocky basement made of basalt lava, and there's your VRL, your volatile rich layer, which they think contains a lot of salt. And we'll worry about where the salt came from in just a second. So how do we know there's an ancient buried rock basement? Because the gravity map here, this is for the Borealis chaos area, see the scale bar, 500 kilometers, and these red and orange blobs. That gravity map shows those localized mass anomalies in red and yellow that are interpreted to represent ancient, now buried, impact craters that are older than the salt layer. So there has to have been rock there to actually be impacted to form the craters. In B, the next layer, this one here, it shows that part of the salt-rich layer was buried under even younger basalt flows, but not everywhere. So there's a basalt cover flow on top of the salt, on top of the ancient basement, but not here. Here, the volatile rich layer is still exposed. In C, here, this is what happens when more bolides impacted Mercury. The impact craters in the younger basalt lava remain discrete with peak rings, while in the areas with no basalt lava to reinforce the surface, the impact craters tended to collapse and coalesce into one another in a chaotic jumble when the volatile salt volatilized or sublimated and created buried cavities that collapsed on themselves. And that's what they're trying to illustrate here, and moving on to here eventually. And in D, finally, the salt glaciers formed in the discrete impact craters in the younger basalt flow fields here, while the chaotic terrain formed where the protective younger basalt lavas were absent, forming those vast areas of surface collapse, such as Borealis chaos. Okay. If Borealis chaos formed because the salt layer was exposed by bolide impacts and it volatilized into outer space, why can we see salt glaciers still in the impact craters? And it's quite simply because the salt in the glaciers was mixed with rock. When the salt sublimated, we're left with what is in effect a rock glacier. In other words, a glacier fossilized in rock. So do you see where I'm going with this? If something as vast as Borealis chaos, if something as vast as this is underlain by a salt-rich layer, just how widespread might such a salt-rich layer be? If it's planet-wide, as the authors of this paper speculate, just how could that happen on a dry planet like Mercury? Terrestrial salt plains, for example, form in lakes and shallow seas. I'll come back to that in just a minute. So this looks like a great story for Mercury, but how do these glaciers compare with glaciers known from elsewhere in the solar system? Well, here's a comparison by the authors between salt glaciers on Mercury and an ice glacier on Mars. This is the example from Mercury, and here's the example from Mars, which actually is a rock glacier because the ice which was involved here has actually sublimated. But you've got the same thing. There you've got the high topography, you've got the edge of the outflow with folds forming in it and pits. And you've got the same thing here. You've got pits, there's the edge of the outflow, and you've got folds towards the end, the edge of it. And a salt glacier. This salt glacier is from the Zagros Mountains in Iran on Earth. Now, I think that the first two are fairly easy to see. Both show something viscous that has flowed down a slope with folds at the bottom of the slope and sublimation pits, as I've just shown you. But the Iranian example is a little more difficult to see. So I went and found a NASA image from the same area in Iran so that you can better see the central salt dome. There we go, right there. That's the highest topography. And the salt that flowed away from the topographical peak of the salt dome and piled up in these ridges. Actually, they're folds. And the steep convex upward slope, as you go from there to there, it's actually a steep convex upward slope that ends abruptly at the edges, here, ends abruptly at the edges of what is considered a classical salt glacier. And there is the original Iran example from the paper. This, I think, is just easier to see, but it's exactly the same process and phenomenon. So, okay. How on a dry planet like Mercury could regional scale, potentially global, salt-rich layers possibly form? On Earth, we would invoke the evaporation of vast, warm, shallow seas and lakes. But how do you do that on Mercury? What would be the source of the salt and what would be the source of the water to form shallow seas and lakes? The authors of this paper examined this question pretty thoroughly. The sodium in the salt, remember it's sodium chloride, could be derived by the breakdown, the weathering of sodium-bearing minerals that make up the basaltic crust of Mercury. Things like feldspars and pyroxenes and amphiboles such as hornblende for those that are in the know. Yes, I know the slide says calcium silicates, but sodium occurs in calcium silicates anyway, so it comes to the same thing. However, it's their interpretation of the source of the water that came as the great surprise for me. One obvious potential source would be the outgassing of a primeval magma ocean as it cooled and crystallized at the end of the original accretionary phase of the planet. But given the existence of an ancient, heavily cratered, solid rocky basement beneath the salt layer, that's not possible. It was already solid. So the next option is that the water came out from the outgassing of the mantle of Mercury through volcanic activity and the massive volcanic outpouring of basaltic lavas that we do see at the surface. And now comes the best part. The authors of the paper suggest that this outgassing gave rise to a water-rich temporary atmosphere of hot steam that collapsed as it cooled. By collapsed in this context, they mean that as the temperature dropped, the atmosphere condensed from a steam bath to surface water that was sufficiently voluminous to form vast shallow seas and perhaps lakes. Now that set me back on my heels in the context of a now dry planet like Mercury. And that's what I call a real change of perspective. So what do you imagine an early Mercury covered by shallow seas might have looked like. Well, how about this artist's impression of just that? The blue here is meant to represent water. It's going to be a pretty evenly shallow sea right the way across Mercury, because Mercury doesn't have high mountains and deep valleys like some other rocky planets. And to be honest, I can't find my way around on this. I've tried. And so I'm a little unclear on the geography, but it just gives you an idea of what this very temporary ocean might have looked like before it evaporated and left salt deposits behind, if that, of course, is indeed the case. So there you have the story of salt glaciers on Mercury. But when did this evaporating salty sea occur? The salt layer, salt-rich layer, sits on an older, already heavily bombarded basement, probably made of basalt lava. It's partially covered by further outpourings of younger basalt lavas, and then is well and truly beaten up by more heavy impact bombardment. So when did all this heavy impact bombardment take place in the history of the solar system? You already know that. I've been telling you about it for the last 20 years. At the very latest, prior to 3.9 billion years ago, and maybe well before 4 billion years ago. So this story is very old, and it relates to the very earliest days of the solar system itself. All this to say that these are exciting times to be following planetary geology. Just when you think you've got a good grasp of what's going on, you can get quite the surprise. As always, thanks for listening.
We do have time for a couple of questions for Simon. I know I have. Anyone else want to go first? Don't worry.
The power switch is on the bottom of that microphone.
With respect to Mercury, no, which is why they've been kicking around so many candidates. As I say, ranging from carbon, they can detect carbon, but with respect to the actual hollows themselves, sulfur is a good candidate, and so is potassium. But none of them tend to go blue when weathered, whereas sodium chloride does. So it's a hint that it's not out of the question. So that coloring, no, that's not NASA playing around with their palette. That is the color. It's probably enhanced, but yes, it is bluish. Yeah.
Anyone else? All righty, with that, thank you. And Dave, what am I doing wrong? Okay, so break time, trivia challenge, rest of the museum is closed, but the restrooms are available. Door prize tickets are here. I'll put the little box out in a moment. So everyone's free to come down and take one from me. Your question to contemplate tonight: which is the only country to have launched an artificial satellite named after an animal? And for extra brownie points, the gold stamp and a crown, what was the animal? So you've got 10 to 15 minutes. Thank you. Dave, do we have any answers coming in online as to the answer to the...
Hang on a second, let me just check. We do. Let's see. Canada Alouette satellite.
Anyone in the audience have that? Okay, all you smarties. Now, what is alouette? More specifically? It's only half kudos points at this stage. Dave, next slide, please. It is a skylark, not a mudlark, not a swallowlark. It is a skylark. We're there. Okay, see, I know something. That's all that proves. All right, Jim. Time to talk about favourite toys. Volcano making tomorrow.
Much this is guaranteed to work now.
According to him up there.
Right. Well, good evening, everybody. And welcome to my talk entitled SHO on the Cheap. Although this title may seem like nothing special, you'll have to take my word for it that it is a lot better than the first title I came up with. What to do if you want to try narrowband imaging but have a one-shot color camera and don't want to buy a new monochrome camera and a filter wheel and all that other nonsense. So let's begin with this pretty picture of the Eagle Nebula captured using the Hubble Space Telescope. The Hubble collects image data for each gas emission separately, including sulfur, hydrogen, and oxygen. This data is then combined after the fact to form a synthetic image, one that does not actually exist in nature. This method of imaging has many advantages for us amateur astronomers, but I'm not going to tell you about any of that. You'll have to tune in next month when Malcolm Lauro gives his amazing, mind-boggling talk about narrowband imaging. In the meantime, though, what if us one-shot color camera owners wanted to try creating an SHO image, sulfur, hydrogen, oxygen? Is there anything we can do? And the answer to that question involves one of my favorite things. Now, I'm sure you're all thinking, well, we all know that Jim really loves many refractors. But what does that have to do with SHO imaging? Well, as it so happens, I have another favorite thing. And that is multi-narrowband filters. I'll be signing posters of that later if you want. Multi-narrowband filters are designed to have two or more narrow passbands centered around desirable nebula emissions. They maximize nebula contrast by blocking as much light pollution as possible. Because they pass light in both the blue-green range of the spectrum and the red range, they produce full-color images with a one-shot color camera. These filters make electronically assisted astronomy and imaging from a light-polluted backyard possible, which is why I have interest in them. Take, for example, there's an extra click in there. Take, for example, these images in the lower left. The leftmost image was collected from my backyard. It's about 10 minutes of exposure, but with no filter. And then the image to the right of it was taken from the same location, same evening, with a multi-narrowband filter, same exposure time. I've removed the stars to make it easier to see the difference in the nebulosity. Multi-narrowband filters have become quite popular in the last couple of years, and there are many brands and models available today. This graph presents all of the MNB, for short, filters available commercially, plotted according to the width of their passbands. The dot color represents the cost of each filter in US dollars. I have a long history with these filters, having tested more than half of those shown here. In my experience, The narrower the filter's passbands are, the more it is able to increase nebula contrast and signal-to-noise ratio. These filters were developed primarily for use with one-shot color cameras, but they also work very well with monochrome cameras. I have a couple more example pictures here to show you what can be achieved using them. All of these are 10-minute total exposures captured from my Boreal 9+ backyard in the Alta Vista area. This shot is of the Eastern Veil Nebula, and it was captured just this past summer. This one of the California Nebula was captured during one of the very few clear nights we had in November. And this final shot is of Thor's Helm that I captured just this past February 5th. Using a multi-narrowband filter with my EAA setup, there is pretty much no limit to what I am able to observe from my backyard. Besides cutting through light pollution to get a wonderful view of nebulae, there is something else that we can do with MNB filters. We can use them to turn our one-shot color cameras into hyperspectral imaging systems. It so happens that emissions captured in the O3 band of the filter are picked up only on the camera's green and blue color channels. And similarly, the hydrogen alpha emissions are only picked up on the red channel of the camera. Thus, the use of the MNB filter helps us to cleanly separate these two emissions from each other. My arrows are out of sync here. I can further demonstrate what I mean by deconstructing this image of the Western Veil, captured again last summer. If I extract just the green color channel from the image, we can see just the O3 emissions by themselves. Similarly, by extracting the red channel, we can see just the H-alpha emissions. So using the filter in conjunction with the color camera, we're able to easily separate these two emissions out of one image. But there's a lot more clicks here. I think the animations in the importation will work on that. What about sulfur? Well, unfortunately, sulfur too emits in the red part of the spectrum, just like H-alpha. So if we want to capture it, we are going to need to take a second image with a different filter. Lucky for us, that has already been done for us. Filter manufacturers have already started developing custom multi-narrowband filters, the ones that we would need to take that second picture to get sulfur 2 by itself. This table is a summary of the multi-narrowband filter pairs that are commercially available today, along with some of their properties such as the bandwidth and the price. At the top of the list, the IDIS NB2 NB3 pair were the first of these types of filters to be sold, being available since around the late 2020. The ASCAR and Altair offerings are all very recent additions to the list, being released within the last 6 months. The sharp-eyed amongst you has probably already noticed that there is a large range in price of these filter pairs, a property that is directly related to the quality and capability of each brand of filter pair. I have had an opportunity to try 2 brands of MNB pairs, the first being the IDIS pair that I played around with about 3 years ago. This is how the NB2 filter image looked, a stack of 15 20-second sub-exposures captured from my backyard. When we split this image's color channels, we get this: red, green, blue. The second image captured using the NB3 filter looked like this. And when we split it into channels, we get this. To assemble my SHO image, I used these 3 color channels circled in red, green, blue there, and I ignored the rest. This was my end result. I found the S2 emission to be weak relative to O3, which made picking the best sub-exposure time difficult. The weak S2 signal also meant that a lot of stretching was required of that channel in order it to be visible next to O3 and H alpha. And that resulted in the image being a lot noisier. If anyone was wondering, I believe this IDIS pair might be discontinued, as the normal reseller in the US, AstroTrivia, no longer markets IDIS products. I think there was some sort of bad blood there. If you come across a set of these used or maybe old stock somewhere, you should note that because they have low off-band blocking, so that's the efficiency with which they are blocking light outside of the band, because that is relatively low, they do tend to have halos on bright stars. My second attempt was made more recently using the Andrea brand pair. This is the image I captured of the Cygnus wall, part of the North American nebula, captured using the normal ALP-T filter, a stack of 5 2-minute sub-exposures. And this is what we get when we split that image into color channels. The image generated by the second filter in the ALP-T pair looked like this, kind of snazzy with the blue. And then when we split it into channels, we get this. To assemble my SHO image, I used these 3 channels and ignored the rest. And here is my resulting image. The contrast and detail in this image is much better than that captured using the IDIS filter, because this pair has much narrower pass bands. The IDIS is in the 30 to 20 range, and this is 2 bands 5 nanometers wide, so quite a bit narrower. I found that Andrea's idea of pairing sulfur 2 with hydrogen beta instead of O3 was a good idea, because it made it easier to manage the sub-exposure time with that particular filter. Unfortunately, this filter pair is 3 times the cost of the IDIS pair, although the total price is still significantly cheaper than having to buy 3 filter narrowband SHO set in entirety. You're buying 2 instead of 3 filters, basically. I've encountered some limitations when using these filter pairs. The first related to camera resolution. Due to the bare matrix applied to the One-Shot Colors camera sensor, only a quarter of the pixels in the sensor are actually collecting red data. Oh, the image is there. Nope, it's not. Okay. Had a graphic there. It'll be there eventually. So yeah, only a quarter of the pixels are collecting red data and only half of the pixels are collecting green data. If we were using a monochrome camera with 3 separate SHO filters, we would be collecting data in each band on all of the pixels in the sensor. The next thing that I found was a problem was setting sub-exposure time and total number of frames. It was a challenge. A nebula's emission of O3, H alpha, and sulfur 2 are not of equal strength. So, ideally, I should have been using a different sub-exposure time and a different number of subframes with each emission to get the same signal-to-noise ratio. But since I was capturing two emissions at the same time with the same exposure, it is often the case that one of the emissions is underexposed so that the other one is not overexposed. The last thing to note has to do with availability of these filters. There are numerous choices of narrowband SHO filter sets available today at a wide range of prices, but only the MNB filter pairs that I listed earlier are available at the moment. So the choices are limited. Oh, there's the graphic. Hello, graphic. You can see what I mean by the bare matrix. Only a quarter of the pixels are red, half of them are green, and the other quarter is blue. My final comments on this idea of using a MNB pair with a one-shot color camera to produce an SHO image are as follows. The experience was actually kind of fun. It gave me a new way to look at and better appreciate some of my old favorite deep sky objects. This was, however, at the expense of more time doing post-processing. Not every emission nebula has a Purdy SHO image waiting to be discovered. Sulfur-2 is not prevalent in every nebula, limiting what objects can be imaged in this way. It may not be obvious from my output images, but if you zoom in, you will see that all my stars are really messed up. Bloated and miscolored and just crazy looking. So a lot more care is required to get nice looking stars in an SHO image, essentially by post-processing the stars separately from the nebulosity, a time investment I am not sure I am willing to pay. And that concludes my presentation. Any questions? You can't actually see anybody in the audience. The spotlight. Oh yeah, way over there. Yep. So for example, oxygen 3 is what's collected by both of the filters, and the blue and the green. So because the blue channel is only collecting, like I said, 1 pixel out of 4, it's not as good a resolution data set as the green channel. So I always preferentially chose to keep the green channel from any of the filters and ignoring the blue. And then when there was 2 filters that both had O3, like the IDIS pair, it had both of its green channels for the 2 filters was O3. I just looked at the data and picked what was the best looking data set. Some of it was cleaner than the others. Any other questions? Oh, one up there.
I think it was last year I saw, I believe it was a YouTube video on processing. And if I recall right, what they were doing the same thing just with software. That there was some software scripts that could analyze the ratio of colors and sort of estimate how much sulfur and how much hydrogen, H alpha, and then they would separate it that way. Did you hear anything about that, or? This was something I saw like 6 months to a year ago, and I don't have all the details, but that's what I recall.
I haven't heard about that, but sort of related, or maybe not. There is a filter that exists. It's called a quad band filter, and it actually has 4 narrow bands that cover hydrogen beta, oxygen 3, hydrogen alpha, and sulfur 2. And it was very popular for a while, but it was very expensive. It's over $1,000 US. And I didn't understand the interest in it because the reality is your camera can't distinguish once it's been collected, everything that comes in on the green channel, it's now all green. Whether it was H beta or O3, it doesn't know. It just collects all that light. And similarly, hydrogen alpha and sulfur 2, and if there's nitrogen 2 as well, that all just gets collected to the red channel. So once that image data has been collected by the sensor, there's no way to separate it after the fact. So to be able to get sulfur and hydrogen separated, you have to take at least 2 images with 2 different filters. There is no way in post-processing to take a color image and divide those channels out. I don't know if that's related to that question or not, but. All right, that's it for me. Thank you very much.
And next up, David with his low-cost solar viewer. Do you want me to move the camera?
In a minute. I brought the image up there so you can adjust it. Yeah, so we're on the lines of going cheap on things. One of the things that was frustrating me, I'm doing a lot of outreach to schools and stuff. And yeah, I could show the kids how to make a little pinhole camera with a cereal box and a piece of paper, but the image is pretty small. And I said, I got to be able to do better than that. So I happen to have a 10 times jeweler's loop at home. So one day I just went out, held it up to the sun, and then just sort of pulled it away a bit to see how far away I would have to go in order to get a good image of the sun. It was about 15 inches. And I said, oh, okay, I've got a solution here. So I built myself this little solar viewer, projection viewer. And as you see here, it cost about $18 in parts from Home Depot. I did not get the jeweler's loop from there. I got that from Amazon, but I only paid $4 for the jeweler's loop. As a result, you'll see there's a lot of artifacts on the image of the sun, but who cares? Well, for an eclipse, we just want to see the moon coming across the sun. And if kids get really excited about it, you just tell them they're sunspots. No, I wouldn't do that. So these are the various parts that comprise of this. There's the most expensive piece actually was the strip of aluminum, which you can see on the front of the unit here. I bend it at 90 degrees. There's a little hole through there, and it tells me when I'm pointing at the sun. The rest of the stuff was relatively inexpensive, and the jeweler's loops they come in 3 packs, so $12 for 3 of them, so $4 each. Basically, I cut the piece of aluminum, bend it 90 degrees in the middle, and drill 3 holes for the mounting screws, and drill a small hole. And you can see in this picture here, you can see the sun reflected above the center screw there. That means you're pointed at the sun. Very simple way of doing it. You don't want the kids looking at the sun to try to align things. Then I cut about 18.5 inches off of my poplar board, mounted the aluminum alignment piece at one end, the board in front of it, and then another board at the end. And then I drilled a hole in the one sheet to accommodate the jeweler's loop. Unfortunately, I didn't have the right size drill, so there's a lot of rough filing to make it the right size, but fits in there nice and tight. Cut your 2 foot by 2 foot plywood sheet into quarters, and you have enough wood for 2 solar viewers. And then you drill a hole in the middle bunch. Oh, I've already talked about that. Yes, I've duplicated myself here. Sorry about that. Let's just move on. So the other thing is you want to make sure that it's balanced on your tripod here. So I just basically laid it on a pencil, rolled it back and forth until it was balanced, marked that point, and then drilled a hole and put a T-nut, which is basically a nut that you hammer into the wood. It's got the same threading as a tripod. And then I spared no expense on the cardboard shade there. My wife and I volunteer at the food bank, and we have lots of these egg boxes, and they're the perfect size. They're 1 foot by 1 foot. So I basically use that as my shade. This one's a little too short. What I'm probably going to do is use almost the whole box. The next one I build, so that it's a little darker inside there. And then I don't know whether you can, you can sort of see the size of the sun on the back of the there. That's why I need a little more shading, so you can see it a little more clearly. The screen is a full page label that I just stuck to the back of to the board there. And yeah, as I said, inexpensive jeweler loops create many interesting artifacts. But I mean, for showing the moon going across the sun, it's great. And it's a reasonable size as well. And I just went too far. So Mick, if you can just hand me one of those packages there. So if there's folks here that are doing outreach to larger groups and you'd like to build one of these, this is like a seed package. All you have to do is add wood instead of water. All the pieces you need to build the solar viewer are in here, the bent aluminum, all the screws, the loop, the two little right angle brackets for mounting the wood. So if you are doing, I would like to give these to folks who are doing a bunch of public outreach things. I've got 2 left here, and you're welcome to take this home and build it yourself. There's detailed instructions in the upcoming Astro notes as well. So I've got 2 here. Just see me after the meeting. And as I said, it cost $18, and it seems to work pretty well. I guess I'll find out on the day of the eclipse. Thank you.
All righty, Richard, please.
Okay, thank you. So, first of all, a big thank you to Oscar for doing the monthly challenges for so many years. These were last month's challengers, the beginner object NGC 2346, the intermediate challenge IC 2177, the Seagull Nebula, the advanced challenge UGC 3933, and the lunar challenge, the crater Proclus. So we'll have to wait a couple of minutes until we get the observations for this month to see if anybody got pictures of those. Anyway, I really have been enjoying the monthly challenges for so long now that when Oscar said that he had to retire from the job, I thought about it for a while and then said, I'll do it. And so I'm going to take on this, the challenge of coming up with challenges every month. But of course, I've got to mess with success, so I've got to mess with how we're going to do the monthly challenges. So I've got a few ideas. I've been posting them on the Discord server and hoping to get some feedback. I had a bit of feedback from some people. So, whoops, we're going into the observation reports first.
Although I can suggest you click through.
Can I jump ahead to the next one on monthly challenges? Oops. There we go. Okay. So here's my ideas for the observing challenges new format for it. So one of my main goals, I think, is to try and get more people involved. I mean, we've got some lovely astrophotos every month, but we haven't really heard from people who are doing visual observations, and especially from, you know, people who are just starting out with observing the night sky for the first time, or just trying to get into understanding constellations, where to find things and that kind of thing. So I'm going to introduce a new kind of level 1 challenge, which will be basically to find something just by looking up in the night sky. So accessible to everybody. You don't have to take a photograph, or if you do, you can just use your cell phone or a little camera like this on the tripod. So something simple and easy that everyone could participate in. I would like to collect observations from people, so I'm suggesting that you send it using the Discord server or by email. You don't have to stand up here and talk to the audience if that's something that's holding you back. Level 2 would be something with minimal equipment, maybe a camera, maybe a pair of binoculars, something like that. And you should be able to spot something fairly easily, but it's a little bit more challenging. You do have to have equipment. We have equipment. If you're a member, you're free to borrow things from our Ted Bean Loan Library. So maybe you'd like to try and do that. Level 3 will be challenges which require a little bit more skill, a little bit more equipment, something a bit like a telescope, maybe something to a go-to mount to help you find something in the sky. And then level 4 will be the really advanced stuff where you need definitely some good quality equipment, tracking mount, guiding, and long exposure photographs, or you'd have to use a big telescope and very careful observations. Lunar Challenge, I'm sorry, Brian. Brian McCullough has always been very much in promoting moon observations, but I'd like to branch out a little bit more, do some more solar system observing. So we'll have a solar system challenge rather than a lunar challenge every month. So as I say, you don't have to stand up here and show astrophotos that you've taken. You can just do a visual observation. You can try things out, see what you can do. Use the Discord server. We've got a section already set up there for monthly challenges. So I will put the month's challenges objects on there, and you can put your observations there too. If you still don't want to do it in public like that, you could send them to me. My email is richard@teya.ca, but please use the subject line RASC Ottawa challenges so that I'll know what they're for. Or you could still present it at a monthly meeting if that's what you like to do. I do want to try and promote careful observations. Like Rick was saying earlier about the Blaze Star, you really should be getting into the habit of recording how you took your observation. So your name, what object it was, the date, the time, where you did it from, the location, what equipment you used, the sky conditions at the time. Describe what you saw or take the photograph. And if you did take a photograph, what did you do afterwards to enhance it? So give some detail about your observation. This is what scientists are trying to do. This is what astronomers try to do. So here are the challenges for the month of March. First of all, let's get out there. Go outside after dark, look up in the sky, and right now, Gemini is way up in the south, very high overhead. It should be easy to find because there are two nice bright stars fairly close together. But what else can you see? Can you see the line of the arms across below the heads? Can you see the lines of the hips or knees? Can you see the feet down at the bottom? This is a good test of how well you can see, but also how badly light polluted the sky might be. Because if the sky is very light polluted, you're not going to be able to see the fainter stars. But which ones can you see? Can we get some observations from all over around Ottawa and the surrounding areas? Where is it easy to see all of these stars, or where can you not see them? Because like Rick was saying, sometimes it's a good observation to know what you can't see. Now, within this constellation of Gemini, there are some fairly interesting objects. For level 2, you'll need a pair of binoculars, at least for this. There's a lovely open cluster of stars, a little fuzzy patch down near the feet. And that's a Messier object M35 down here. We've had this as a challenge object before, but it's a nice cluster. It's something that you should be able to see fairly easy. So see if you can find it. How did you find it? And what did it look like? A bit more of a challenge is Caldwell 39 up here. This is quite a small object. It's what's called a planetary nebula, and sometimes called the Clownface Nebula. It has another catalog number, NGC 2392, but that's going to require probably a telescope to see that. It's quite small. It's called a planetary object because it kind of looks a bit like a planet. It's fairly bright, but quite small. And then for the real keeners, somebody with a long exposure photograph might be able to get the Jellyfish Nebula down here. This one is not a challenge because it's so small, it's a challenge because it's so faint. You probably will not be able to see this with your eye, even through a very large telescope. Or can you? Find out. But a long exposure photograph with a modest telescope should be able to see this. So let's see what you can do with those objects in the constellation of Gemini. For the solar system challenge, Dave has just been talking about how can you get an image of the sun. Good time to practice before the eclipse coming up. So your challenge here is, can you produce some kind of viewer or photograph or something that you can see sunspots? Here's my example. I built a similar little cardboard box off the side of my Tasco department store refractor. And yes, I could see sunspots with it. What can you do? Can you make something so that you can get pictures of sunspots, or at least see some sunspots? And don't forget, there's also this extra challenge that Rick talked about. Start looking at Corona Borealis. If you can find this little constellation, it's just beside Boötes. See if you can see the stars from somewhere around Ottawa. And is there an extra one? Somewhere there? If you see that first, you win the prize. Okay, so those are the challenges. And as an extra bonus, it is clear tonight. So I brought along my little camera on a tripod, and after the meeting, I'll be out front and we can give it a try right tonight. Can we see Gemini? Can we take a picture of Gemini? So that's all for me tonight. I'll see you next month, and please, I hope to see some observations on the Discord server. Or I'll be outside in 20 minutes.
Great. Dave, can you back us up to the... Done. Done. Oh, good man. Thank you. Anyway, that's great, Richard. I love the innovation. So hopefully you get some good uptake here. All righty, Bob, would you please come to the podium? I'll do it.
Sure, go ahead.
You watch me.
Next.
Watching.
Yeah, sure.
Okay.
Okay, this is M63, the Sunflower Galaxy. It was visible for me for 3 nights in February. And one of those nights, though, was the moon was washed out the imaging. So that was useless. So I got 2. I ended up with 3 hours of data. When I was filing the images on my computer, I noticed that I had also imaged M63 in 2020, 2021. If I used this data, I would have 28 more hours, obviously clearer in 20 and 21. So that's what you see here on the screen. So it's based on 3 years of data, 31 hours. Yeah. The Sunflower Galaxy is the same part of the sky as 3 of my favorite galaxies. These are 64, the Black Eye Galaxy, M101, the Pinwheel Galaxy, and M51, the Whirlpool Galaxy. These galaxies are now rising in the east and will continue to get higher in the sky until they reach the zenith in June, at which point they'll be almost overhead. Get a telescope and take a look at them. They're worth the view. Next image, please. On February the 14th, I was able to get 3 hours of exposure on the Butterfly Nebula. This planetary nebula has a visual magnitude of 9.6, which means you should be able to see it in a telescope. It is about 2,000 light years from Earth. Next image, please. Crop it in a bit. The central star of this planetary nebula is actually a binary star. When one of the stars evolved into a giant red, it got large enough to engulf its neighbor. Sort of what's going to happen to us when the sun gets bigger, going to engulf the Earth. The companion star then spiraled down inside the red giant, creating the butterfly shape of the nebula. Thank you.
Thank you. Need to click it.
Sure. Okay. Hi, folks. So the next 4 images that I'm going to be showing you, I took from my downtown balcony using the Antilla quad band light pollution filter, the 8-inch Smith Cassegrain telescope, and the Mellencamp Skyradar camera. All images were live stacked under 10 minutes of total exposure time and post-processed afterward using Topaz Studio 2. So the image you're seeing now is M82, the cigar galaxy in the constellation Ursa Major. M82 experiences gravitational interactions with its neighbor M81, causing it to have an extraordinary high rate of star formation. Hence it is called a starburst galaxy. M82 is 12 million light years away and was discovered along with its neighbor M81 by Johann Bode in 1774. And this is IC63, the ghost of Cassiopeia, 550 light years from Earth. It's an emission and a reflection nebula about a third of a degree northeast of the star Navi. I captured some of the hydrogen emissions from a nearby blue giant star, which is not in view, but the full image of IC63 I took off the web and appears on the lower right. Next image is the Bubble Nebula, NGC 7635, which is an emission nebula in the constellation Cassiopeia. It is 7 light years across and 8,000 light years distant. The bubble is sculpted by the stellar wind from a nearby massive star, which is sweeping up cold interstellar gas in front of it, which forms the edge of the bubble. The Bubble Nebula was discovered by William Herschel in 1787. And last but not least is NGC 1491, the Fossil Footprint Nebula, which is an emission nebula about 9,800 light years away in the constellation Perseus. And it gets its deep red coloration from the many massive stars embedded within it, which produce large amounts of ultraviolet radiation and ionized hydrogen gas. Thank you.
Okay, Richard again.
Okay, so I haven't really been out observing much this last month. It's been either too cold or too cloudy most times, but Valentine's Day was wonderful. Beautiful clear night that night. So I went out fairly early in the evening while the sky still looked a little bit blue and the moon was just beautiful up overhead. So I immediately started taking a couple of short videos of the moon. And it turned out wonderfully. My mount tracked beautifully, it aimed precisely. Everything was going so well. I was really excited for a good night ahead. But I remember there was the challenge object on the moon, the crater Proclus. So zooming in on that and sharpening it up a little bit. There it is, that little crater on the edge of Mercury. And it actually becomes quite prominent later on in the month when the moon is full. But at this point, you can just see a little bit of one of the rays coming out of it. But later on, it gets really very, very bright. So then I thought, okay, I can go for one of the objects that I've been waiting for quite a while, the M77. There's a galaxy, and it's sort of in Cetus, I believe it is. So it was heading towards the west. It's probably not going to be visible much longer. And that's when my luck started to fail. Because when I started imaging on this galaxy, I got these weird stripes, and I looked up and oh, right in the power lines. And I've been hoping to get a nice combined view. Oops, sorry, no, back again. Can I go back? I was hoping to get both this galaxy and this little sideways or spiral galaxy, which is NGC 1055. But they were in amongst the power line, and even worse, as it was tracking along, it wasn't moving out of the power lines. The power lines were aligned directly with the rotation of the Earth. So I got nothing. I got 6 images, and then I just gave up. So this is the best I could do with post-processing. Not a great one. I will have to come back to this target later on. It looks quite fascinating. It's got a lot of different intensity. You got this fuzzy outer arms, and then some very bright stuff in the core, and a very, very, very bright central core on the galaxy. So worth coming back to some other time or from FLO. And then I thought, okay, well, the other challenge object was the Seagull Nebula. That should be visible now. So I shifted the telescope over and aimed at that, and it was right in a tree. So I took dark frames for a while, waiting for it to come out of the trees, and eventually it did, but there was only a very short gap between 2 trees. So I got 15 2-minute exposures, and that was it. So we're not seeing all the lovely red wings of the seagull. We just see this really weird looking head with a very bright eye and a big smiling mouth, and it looks actually more like Woody Woodpecker, I think, rather than a seagull. But that was the best I could do. I think I'll just hibernate again until it gets warmer. Thank you.
And Jim, please.
All right. So the first couple images I have tonight were from the only deep sky observing session that I've had in the last 3 months, occurring on February 5th from my backyard in central Ottawa. This first pair is of the well-known object M42, the Orion Nebula. The images were captured simultaneously using 2 different setups on the same mount. On the left was my ASI 533 MC Pro camera with Optolong L Ultimate multi-narrowband filter, one of my favorite things, on a 10-inch Ritchie-Chrétien scope reduced to f6. On the right, the image was captured using my Malincam DS432M with an Antlia 2.5 nanometer H-alpha filter on a, you guessed it, mini refractor, an ASCAR FMA 230. The color image is a live stack of 99 10-second exposures, and the monochrome image is a stack of 30 30-second exposures. So 15 minutes exposure total for each of these. I was especially pleased by how well the gas and dust that surrounds M42 came out after only 15 minutes of total exposure time. Keeping in mind, this is from my backyard in Alta Vista, where on a good night, I can see about half a dozen stars. I would fail your challenge, by the way, Richard. I can see the two brightest stars in Gemini, and that's it. The next pair of images from the same night is of one of the observing challenges for this month, IC 2177, the Seagull Nebula. It's located between Monoceros and Canis Major, which is nicely placed in the south right now. This is a very large, faint object, extending beyond the field of even my mini refractor. As you can see, the right wingtip is clipped in this image. The head of the seagull is the brightest part, as we saw in Richard's image. And that is why the color camera is aimed at that particular part of the object. Being located fairly low in the south also contributes to it being a somewhat difficult object depending on what the local transparency and light pollution conditions are. These are both stacks of 30-second frames, so another total 15-minute exposure. Next, we move on to some solar images, which I had more opportunity to do over the past month than deep sky. This first pair of images, with calcium 2K on the left and hydrogen alpha on the right, were captured on Family Day, February 19th, when I should have been spending time with my family. Seeing was average, and I had to capture frames in between passing clouds. So all things considered, I was pretty happy with what I was able to get. It was also nice to get outside into the sun finally without it hurting to breathe the air. Of interest on this particular day was the large sunspot group in the upper left that we will see more of in a moment, and the active region at the rightmost edge of the sun. Both of these images, by the way, are stacks of the best 200 frames out of 3,000, stacked in AutoStacker 3 and sharpened using IMPPG. Color was added after the fact. I used a monochrome camera to collect the data. This next image is an enlargement of that active region I mentioned. I felt it was noteworthy because of how bright it was and how rapidly it was changing shape. The image here on the left is captured using calcium 2K. Two spikes of hot gas can be seen jetting out of the sun's surface in the area of the rightmost active region near the limb. Right here. One jet, two jet. Prominences are not normally visible in calcium K. So these jets would have to have been very, very hot. The two images on the right were both captured using hydrogen alpha, but at different exposure times. Even at the very fast exposure time, so as to see the surface detail in the middle image, the spiky prominences are clearly visible right here. The longer exposure, taken only 4 minutes later, shows that the shape of the prominence had changed dramatically. Normally it would take, tens of minutes to a half an hour to see that kind of change. It would have been great to have done a time lapse of this area, but with all the passing clouds, that was just not going to be possible. So unfortunately, this is the best I could do. I had another chance to image the sun 5 days later on February 24th. On this day, the large sunspot group that was just rounding the sun's limb on Family Day, active region 13590, was now well placed along the sun's meridian, the middle line of the disk. Although it was a very clear day, seeing was poor. These images are stacks of the best 200 frames from 5,000. This sunspot group has been very active, spitting out lots of solar flares and all kinds of neat stuff. To say that the sunspot group was large was a bit of an understatement. It was clearly visible to the naked eye with eclipse glasses, for those of us who were able to get out to see it. My final image is a close-up of this active region, taken the same day using a Bader solar continuum filter. That's a narrow band pass around 540 nanometers in the green part of the spectrum, combined with a 2.5 times Barlow. I was very pleased to have captured such fine detail despite the poor seeing conditions. If you note the two small spots in the lower right, these two over here, the Earth is kind of the size in between those two, to put this into scale. When I imaged the active region, it covered about 4.3 billion, that's with a B, billion square kilometers, almost 10 times the surface area of the Earth. Some other amateurs posting online at the time about this big sunspot group noted that it got to about 60% the size of the sunspot group responsible for the famous Carrington event in September 1859. I don't know if you remember hearing about that, where lightning bolts were coming out of telegraph lines and that sort of thing. Although it is very cool to see something this big on the sun, I am keeping my fingers crossed that we don't get a massive satellite smoking coronal mass ejection from this region like what happened during the Carrington event. Thank you.
And Andrea.
Hello. So there was, only a few days in February, and they were Family Day and Valentine's Day, and we were all out taking pictures. I forget which day this was, but this is the Running Man Nebula, which people often forget because it's next to the more famous Orion Nebula. I actually was trying to shoot the Seagull Nebula, but it was way, way too low for me. I have high trees. This was with the C11, so it's very, very zoomed in, the 2600 mm camera. And I just did red, green, and blue filters, so no narrowband filters. This is natural color. This is a reflection nebula, and it has lots of dark dust. And it was so pretty and three-dimensional that I decided I would do a little star animation, because that's always fun. And so that was one night. So I did about 2 hours in red, green, and blue for 6 hours overnight. This is a dark nebula, LDN 1662, also known as the Boogeyman Nebula. It's up near the Barnard's Loop. It's often photographed wide angle with M78. This was actually a fun project because it was a collaboration with two other people who had the exact same telescope, the exact same camera. And we thought we were going to try to gather all this data and stack everything. But then we were imaging in January, and January was horrible. We did imaging with a photographer from Boston, Marcia, and Dylan O'Donnell from Australia. So we had to pick a target that could be seen from Australia and Ottawa. So we went for the constellation Orion, and we did LRGB and many, many hours of H alpha. This is my process. I haven't seen what the other two have done. It was really hard to process. This is about 28 hours. That's all we got with 3 people. So that's kind of sad. This is something, I think this was the Valentine's Day night. This is the Cigar Galaxy, and I know some other people were shooting it. Jim, obviously, I know Malcolm was. And again, this is with the C11 telescope. And as Jim mentioned, it's a starburst galaxy. So in the core, all these stars are being created and then they explode. And I ended up shooting several hours of H alpha. And I was surprised at how much the red came out. There was an awful lot of H alpha in the red smoky area. And those were, I think that's it. These are my images for this past month.
All right, another innovation. We have a tentative outline for the agenda for next month's program, which is not the May 1st one. It will be April 5th. I'll be talking about the life of someone who really should be much better well known, and that's David Malan. For those that want to do your homework in between. As Jim said, Malcolm Laurel will be presenting on narrowband astrophotography. I'm opening up for a very extended observation report on the assumption that someone will actually get a spot where there's no clouds and have lots of photos that they want to share. So that's sort of it for next month. Yeah, I know, but not if it's on May the 1st. Oscar, aren't you paying attention? No. Now we're both confused. All righty, Estelle's pick of the month, double stars for small telescopes. As I said, library at the back will be available after the program. Redlossing Observatory, for those new to the centre, this is our private observatory out near Almond, very well equipped, reasonably dark skies. Members are welcome with guests. The next FLO Star Party will be on March the 9th, all things being equal. Thanks to the people who keep the club running. Audience tonight, I believe we had 65 here with us in Chasm, and then 35 online.
75,
75.
75, 35 online, 110.
110. So thank you all. Special thanks to all our speakers. And to our hosts for the Zoom service, the RASC National Office. After the festivities, after Richard's Starfest in the car park, post-meeting entertainment, drinkies and food at Liam Maguire's on St. Laurent up near Innes. Next meeting, Friday, April the 5th. There will not be an extended observing report. Oscar has spoiled that fun for me. Just the normal one. And apologies to Paul. Apparently he submitted images on Wednesday evening and I have not received them. So that will definitely be first off the queue next month. So with that, thank you to you all. See you in a month's time, and safe driving and happy observing. Cheers.